So this is my lab 5. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube with aluminum foil. We're trying to model the magnet and tube interaction computationally and compare it to the computational predictions. And as a preview for my findings, my experimental and computational models were the same, but yielded times of 1.376 seconds and 1.378 seconds respectively. So using GlowScript, this lab uses fundamental physics principles, and these include Faraday's law, which states that the induced EMF in a coil is equal to the rate of change of flux, and Lenz's law states that the polarity of induced EMF tends to produce a current which opposes the change in magnetic flux that's produced. And the negative sign in the formula represents this effect. Thus, the negative sign indicates that the direction of the induced EMF and the change in the direction of magnetic fields have opposite signs. Next, magnetic flux is the measurement of the total magnetic field which passes through a given area. So the experimental model uses the app to identify the north pole of the magnet and uses a recording to track the position of the magnet dropping through the aluminum tube. So the system is the magnet while the surroundings is the tube and anything else. For initial conditions, I had the magnet mass, the aluminum foil tube measurements. So in this experimental model, we assume that the bar magnet acts as a magnetic dipole. We also assume that the system is isolated so that there are no other magnetic fields interacting with the experiment. We also assume that the magnetometer app accurately identifies the north pole of the magnet and its other properties. And as for the trials, I found that the average amongst the 5 times was 1.376 seconds, and the magnet falls slower in the aluminum foil tube than in free space because the cylinder exerts an upward force to oppose the change in flux. The computational model uses Python and GlowScript to create a theoretical model of the magnetic field. So for the first part, I just inputted the data from the experimental model, and I also set up methods for calculating the magnetic field of the bar magnet and its flux. The next part calculates the motions of the magnet falling through the tube, as well as calculating the currents that are produced from the flying magnet. It also accounts for forces acting on the magnet, including gravitational force and the magnetic force. So here are the results of Python code. So I got a graph which plots velocity of the magnet against time, and we see that in the output, the time it takes for the magnet to enter was 1.378 seconds. So this graph shows us that there are multiple forces acting on the magnet, which in this case is gravity and the opposing magnetic force. In the top left, the blue coloration of the tube represents clockwise rotation of the current, while the red is counterclockwise rotation. And this is produced because of Lenz's law, which again states that the magnetic field produced by induced currents opposes changes in flux. So from both models, the times were very close, at 1.376 and 1.378 seconds. Some sources of error include measurement errors, and from the app, like in reading the times and the recording itself. There also could have been other magnetic fields interfering with the experiment that couldn't be accounted for. And so to further think about the physics concepts in this lab, we can look at the discussion questions. So we know that resistivity is inversely proportional to the current. So if the resistivity was decreased to U0, then the current would become extremely high and cause the magnet to fall very slowly within the tube. And as for the second question, if there were any holes or slots in the tube, there would be less current rings within the tube itself. Therefore, with less overall current rings, there would be less opposing force within the tube, and thus the magnet would probably fall faster. And that would result in a shorter period of time that the magnet is falling within the tube. Thank you.